Hello everyone and welcome back to JCE Connect. I am Professor Rajendra Jotawar from Jain College of Engineering, and today we will be continuing with the second model of cloud computing, that is architecture for parallel and distributed computing, starting with technologies and distributed computing. Here we introduce relevant technologies that provide concrete implementation of interaction models which mostly rely on message-based communication. They are remote procedure call or RPC, distributed object frameworks and service-oriented computing. Remote procedure call or RPC is a fundamental abstraction enabling the execution of procedures on a client request. RPC allows extending the concept of procedure call beyond the boundaries of processes and a single memory address space. The call procedure and calling procedure may be on the same system or they may be on the different system in the network. You can see in the diagram that the major components that enable RPC system. The system is based on client-server model. The server process maintains a registry of all the available procedures that can be remotely invoked and listens for the request from the clients and specifies which procedure to be invoked together with the values and parameters required by the procedure. RPC maintains a synchronous pattern that is natural in IPC, that is inter-process communication and function calls. Therefore, the calling process thread remains blocked until the procedure on the server process has completed its execution and results is returned to the client side. RPC runtime, on the other hand, is not only responsible for parameter checking and unpacking but also for handling the request and reply interaction that happens between the client and the server process in completely transparent manner. Therefore, developing a system leveraging RPC for our IPC, that is remote procedure for call for interprocess communication, consists of the following steps. That is, design and implementation of server procedures that will be exposed for remote invocation, registration of remote procedures with RPC server on the node where they will be made available, the design and implementation of client node that invokes the remote procedures. Next, we have distributed object frameworks. Distributed object frameworks extend object-oriented programming systems by allowing objects to be distributed across heterogeneous network and provide facilities so that they can coherently act as though they were in the same address space. Distributed object frameworks leverage the basic mechanism introduced in RPC and extend it to enable the remote invocation of object methods and keep track of references to the object made available through network connection. With respect to RPC model, the infrastructure manages instances that are exposed through well-known interfaces instead of procedures. Therefore, the common interaction pattern is the server process maintains a registry of active objects that are made available to other processes according to the specific implementation. Active objects can be published using interface definition or class definitions. The client process, by using the given address scheme, obtains a reference to the active remote object. This reference is represented by the pointer to an instance that is of shared type of interface and class definition. Third, the client process invokes the methods on active objects by calling them through the reference previously obtained. Parameters and runtime values are assembled and arranged as it happens in the case of RPC. Distributed object frameworks give the illusion of interaction with local instances while invoking the remote methods. This is done by mechanism called proxy skeleton. Proxy and skeleton always constitute a pair. The server process maintains a skeleton component which is in charge of executing methods that are remotely invoked, while the client remains the proxy component, allowing the hosting environment to remotely invoke methods through its proxy interface. Next, we have object activation and lifetime. The management of distributed objects poses additional challenges with respect to the simple invocation of procedure on remote node. Methods live within the context of an object instance, and they can alter the internal state of object as a side effect of their execution. In particular, the lifetime of an object instance is a crucial element in distributed object systems. Within a single shared memory scenario, Objects are explicitly created by programmer and their references are made available by passing them from one object instance to another. The memory allocated for them can be explicitly reclaimed by the programmer or automatically by the runtime systems when there is no more references to that instance. A distributed scenario introduces additional issue that requires different management of lifetime of objects exposed through remote interfaces. The first element to be considered is the object activation and the creation of remote objects. Various strategies can be used to manage this activation, from which we can distinguish two major classes: server based activation and client based activation. In server activation, the active object is created in the server process and registered as an instance that can be exposed beyond process boundaries. In case of the object in sorry in this case, the active object has a life of its own and occasionally executes methods as consequences of remote methods invoking client based activation. Remote method invocation. In client-based activation, the active object does not originally exist in the server side. It is created when a request for method invocation comes from a client. The second element to be considered here is the lifetime of remote objects. In the case of server-based activation, the lifetime of an object is generally user-controlled, since the activation of remote object is explicit and controlled by the user. In case of client-based activation, the creation of a remote object is implicit and therefore its lifetime is controlled by some policy of runtime infrastructure. Different policies can be considered. The simplest one is implies the creation of new instance for every method invocation. This solution is quite demanding in terms of objects instances and is generally integrated with some lease management strategy that allows objects to reuse the subsequent method invocations. Another policy might consider having only a single instance at a time, and the lifetime of object is then controlled by number of other frequency method calls. Different frameworks provide different level of control of this aspect. Object activation and lifetime management are features that that now supported to some extent in almost all the frameworks of distributed programming language, since they are essential to understand behavior of distributed systems. Next, we have distributed object framework. The support for distributed object framework has evolved over time, and today it is common feature of mainstream programming languages such as C# and Java, which provides these capabilities as part of base libraries. This level of integration is a sign of maturity of the technology, which was originally designed as a separate component that could be used in several programming languages. Here we briefly review the most relevant approaches to the technologies for distributed object programming. Starting with Common Object Request Broker Architecture, or CORBA, is a specification introduced by Object Management Group, or OMG, for providing cross-platform and cross-language interpretability among distributed components. The specification was originally designed to provide an interpretation standard that could be effectively used in the industrial level. Second, we have Distributed Component Object Model, or DCOM. It's a solution provided by Microsoft for distributed object programming before the introduction of .NET technology. DCOM introduces a set of features allowing the use of DCOM components beyond the process boundaries. A COM object identifies the component that encapsulates a set of coherent and related operations. It was designed to be easily plugged into another application to leverage the feature exposed through its interface. Next one is Java Remote Method Invocation, or RMI. It's an API which allows an object to invoke a method on an object that exists in another address space, which could be on the same machine or remote machine. Through RMI, object running in a JVM present on one computer, let's say on a client side, can invoke methods on an object present on a server-side JVM computer or server-side JVM machine. The RMI creates a public remote server object that enables client and server-side communications through simple method calls on a server object. Last one is .NET Remote. Remoting is a technology allowing IPC among .NET applications. It provides developers with a uniform platform for accessing remote objects from within any application developed in any of the languages supported by .NET. With respect to other distributed object technologies, remoting is fully customizable architecture that allows developers to control the transport protocols used in exchange of information between the proxy and the remote object. The serialization format used in the encode data, the lifetime of remote objects, and the server management of remote objects. Remoting allows objects located in different application domains to interact in a completely transparent manner, whether the two domains are in the same process, in the same machine, or on different nodes. Next, we have service-oriented computing. It organizes distributed system in terms of service, which represent the major abstraction for building systems. Service orientation expresses applications and software systems as an aggregation of services that are considered within the that are coordinated within the service-oriented architecture or SOA. Even though there is no design technology for development of service-oriented software systems, web services are the de facto approach for developing SOA. Web services, the fundamental component enabling cloud computing system, leverage the internet as the main interaction channel between the users and the system. Here, under service-oriented computing, we will be looking at what is service, service-oriented architecture, web services, and service orientation and cloud computing. Starting with what is service. A service encapsulates a software component that provides a set of coherent and related functionalities that can be reused and integrated into a bigger and more complex application. The term service is general abstraction that encompasses several different implementations using different technologies and protocols. Box identifies four major categories that identify a service. Boundaries are explicit, services are autonomous, service shared schema and contact, not the class or interface definition. The service compatibility is Next one, we have service oriented architecture, that is SOA. It's an architectural style supporting service orientation. It organizes a software system into a collection of interacting services. SOA encompasses a set of design principles that structure system development and provide means of interacting components into a coherent and decentralized system. SOA based computing packages functionalities into a set of interoperable services which can be integrated into different software systems belonging to separate business domains. There are two major roles within SOA, the service provider and the service consumer. The service provider is the maintainer of the service and the organization that makes available one or more services for others to use. To advertise services, the provider can publish them in a registry together with a service contract that specifies the nature of service, how to use it, the requirement for the service, and the fees charged. The service consumer can locate the service metadata in a registry and develop the required client components to bind and use the services. Service providers and consumers can belong to different organization bodies or business domains. It is very common in SOA based computing systems that components play a role of both service provider and consumer. SOA provides a reference model for architecting several software systems, especially enterprise business applications and systems. In this context, interoperability standards and service contracts play a fundamental role. In particular, the following are the guiding principles which centralize SOA platform, which categorize SOA platforms which are winning features with the enterprise context. Standard service contract, loose coupling, abstraction, reusability, autonomy, lack of state, discoverability, and composability. Next, we have web services. These are the prominent technology for implementing SOA systems and applications. They leverage internet technologies and standards for building distributed systems. Several aspects make web services the technology of choice for SOA. Out of those, the first one is they allow for interportability. The first, they allow interoperability across different platforms and programming languages. Second, they are based on well-known and vendor-dependent standards such as HTTP, XML, and so on. Third, they provide simple way to connect heterogeneous software systems, enabling quick composition of services in distributed environment. Finally, they provide the features required by enterprise business applications to be used in an industrial environment. Lastly, we have service orientation and cloud computing. Web services and Web 2.0 related technologies constitute a fundamental building block for cloud computing systems and applications. Web applications are the front end of the cloud computing systems which deliver services either via web service or provide a profitable interaction with Ajax-based clients. The entire IT computing stack from infrastructure to application can be composed by relying on cloud computing services. Within this context, SOA is a winning approach because it encompasses design principles to structure, compose, and deploy software systems in terms of service. Therefore, service orientation constitutes a natural approach to shaping cloud computing systems because it provides means to flexibly compose and integrate additional compatibilities into existing software systems. Cloud computing is also used to elastically scale and empower existing software applications on demand. Service orientation fosters interoperability and leverage platform independent technologies by definition. With this context, it constitutes a natural solution for solving integration issues and favoring cloud computing adoptions. With this, we come to an end of second module. Thank you.